In this chapter, we'll talk about two important things related to the simple linear regression model that we introduced in part 1. The first thing we'll talk about is the expected value of OLS estimators. So now that we've estimated beta naught and beta 1, we will talk about their expected values. And we will also talk about the variance of the OLS estimators, beta naught and beta 1. We will introduce some assumptions that are necessary to prove unbiasedness of the OLS estimators, and later we will also talk about the variance. So recall that we've introduced the simple linear regression model, which was essentially a population model, right? So far we've also tried to come up with expressions that are purely algebraic based on a sample of data. Okay. We also showed that residuals average to 0 when we are applying ordinary least squares. Okay, so regardless of any underlying model, if you looked at the residuals and you average them out, they would always equal 0 by the nature of this OLS method. Okay, so now our goal is to study the statistical properties of the estimators, beta naught hat and beta 1 hat, and see, whether there's bias, what do we need to avoid bias, etc. Okay, so before we get into those assumptions, it is important for us to ask the question that how do our estimators behave across different samples of data? So if we had 700 people and we were trying to estimate the effect of education on wages, what happens if we take another 700 people and this is another random sample? What would happen to that estimator, right? That effect that you capture using that slope coefficient. Would that change? What if we kept on taking these different random samples? If we could repeatedly sample in this way, would we get closer to this relationship that exists between education and wages in the population? Okay, so in other words, we're trying to get to this question or this target of expected value or the average of the OLS estimators, right? So what would be the average outcome across all possible random samples? If we had, this is random sample number 1, 2, and we had many of these, would we be right on average, right? That's what we want. And this is sort of what motivates this idea of unbiasedness. Okay, and so we'll talk about 4 conditions that we need for beta naught hat and beta 1 hat to be unbiased. Okay, so we're trying to come up with assumptions that make these unbiased, which is to say that the expected value of beta naught hat is actually equal to the value or beta naught in the population. And similarly, the expected value of beta 1 hat equals beta 1 is saying that if we took the average of these estimators in different samples, that should be equal to what this relationship between x and y is in the population. Okay, so let's talk about the first assumption. So the first assumption we need, we're just going to name these SLR, which stands for simple linear regression. So the first assumption here is that we need linearity in parameters. Okay. In other words, we are able to write out this simple linear regression model that we've been writing out all throughout part 1. And we're basically saying that beta naught and beta 1, they are linear functions of x and y. Okay. Now, beta naught and beta 1 are unknown population parameters, okay? We're basically saying, can we write out expressions for beta naught and beta 1 that are linear in x and y, okay? And so we know what these formulas are, and so of course we can write that down. Now, you might want to think about some examples here, right? So take a look at this equation right here. This is saying that y, which is your consumption, is a function of income, right? How much you consume is dependent on your income level, okay? So this is a very simple model, very intuitive, right? That consumption should be a function of income. And this right here is a model that is linear in parameters as well as linear in variables. Okay, so linearity in parameters is what we really need for that unbiasedness that we're trying to get at. But linearity in variables is basically saying that consumption, let's say, is measured in dollars and income is measured in dollars, right? So that's what linearity would mean. But it would be more easy to understand if we took a nonlinear example of it, right? So let's take a look at this example right here. This equation tells us that, again, beta naught and beta 1 are parameters that can be written out. We can write out beta naught and beta 1 in terms of y and x, right? This is x now. X has changed. So this is still linear in parameters, but this is nonlinear in variables, right? So this is a nonlinear function, a square root, right? So whatever x is measured in, we're basically taking the square root of that, right? So that's not, it's displaying a nonlinear relationship between x and y. Let's take a look at this last equation right here. This is nonlinear in parameters. So if we had written out a model like this is going to violate this assumption of linearity in parameters.